Brainfuck is an esoteric programming language noted for its extreme minimalism. The language consists of only 8 simple commands and an instruction pointer. It is designed to challenge and amuse programmers, and was not made to be suitable for practical use. It was created in 1993 by Urban Müller. Language design: Urban Müller created Brainfuck in 1993 with the intention of designing a language which could be implemented with the smallest possible compiler, inspired by the 1024-byte compiler for the false programming language. Several Brainfuck compilers have been made smaller than 200 bytes. One compiler of 100 bytes is known to exist. The classic distribution is Müller's version 2, containing a compiler for the Amiga, an interpreter, example programs, and a readme document. The language consists of 8 commands, listed below. A Brainfuck program is a sequence of these commands, possibly interspersed with other characters. The commands are executed sequentially, with some exceptions. An instruction pointer begins at the first command, and each command it points to is executed, after which it normally moves forward to the next command. The program terminates when the instruction pointer moves past the last command. The Brainfuck language uses a simple machine model consisting of the program and instruction pointer, as well as an array of at least 30,000 byte cells initialized to 0. A movable data pointer. And 2 streams of bytes for input and output. Commands: the 8 language commands, each consisting of a single character. Alternatively, the command may instead be translated as an unconditional jump to the corresponding command, or vice versa. Programs will behave the same but will run more slowly, due to unnecessary double searching. And match as parentheses usually do, each matches exactly one and vice versa, the comes first, and there can be no unmatched, or between the two. Brainfuck programs can be translated into C using the following substitutions, assuming PTR is of type unsigned and has been initialized to point to an array of zeroed bytes. As the name suggests, Brainfuck programs tend to be difficult to comprehend. This is partly because any mildly complex task requires a long sequence of commands. Partly it is because the program's text gives no direct indications of the program's state. These, as well as Brainfuck's inefficiency and its limited input-output capabilities, are some of the reasons it is not used for serious programming. Nonetheless, like any Turing-complete language, Brainfuck is theoretically capable of computing any computable function or simulating any other computational model, if given access to an unlimited amount of memory. A variety of Brainfuck programs have been written. Although Brainfuck programs, especially complicated ones, are difficult to write, it is quite trivial to write an interpreter for Brainfuck in a more typical language such as C due to its simplicity. There even exists a Brainfuck interpreter written in the Brainfuck language itself. Brainfuck's formal parent language, except for its 2 I/O commands, Brainfuck is a minor variation of the formal programming language *2 created by Corrado bar paragraph HM in 1964. In fact, using 6 symbols equivalent to the respective Brainfuck commands plus bar paragraph HM provided an explicit program for each of the basic functions that together serve to compute any computable function. So in a very real sense, the first Brainfuck programs appear in bar paragraph HM's 1964 paper and they were programs sufficient to prove Turing completeness. Examples: Hello World. The following program prints Hello World. And a new line to the screen. For readability, this code has been spread across many lines and blanks and comments have been added. Brainfuck ignores all characters except the 8 commands plus minus, so no special syntax for comments is needed. The code could just as well have been written as ROT13. This program enciphers its input with the ROT13 cipher. To do this, it must map characters AM to NZ, and vice versa. Also it must map AM to NZ and vice versa. It must map all other characters to themselves. It reads characters one at a time and outputs their enciphered equivalents until it reads an EOF, at which point the program terminates. The basic approach used is as follows. calling the input character x, divide x1 by 32, keeping quotient and remainder. Unless the quotient is 2 or 3, just output x, having kept a copy of it during the division. If the quotient is 2 or 3, divide the remainder modulo 32, by 13. If the quotient here is 0, output x plus 13. If 1, output x 13. If 2, output x. Regarding the division algorithm, when dividing y by z to get a quotient q and remainder r, there is an outer loop which sets q and r first to the quotient and remainder of 1/z, then to those of 2/z, and so on. After it has executed y times, this outer loop terminates, leaving q and r set to the quotient and remainder of yz. Within the loop, there is code to increment or and decrement y, which is usually sufficient. However, every zth time through the outer loop, it is necessary to zero and increment q. This is done with a diminishing counter set to the divisor z. Each time through the outer loop, this counter is decremented, and when it reaches 0, it is refilled by moving the value from a back into it. Portability issues, partly because Urban Müller did not write a thorough language specification, the many subsequent Brainfuck interpreters and compilers have come to use slightly different dialects of Brainfuck. Cell size: in the classic distribution, the cells are of 8-bit size, and this is still the most common size. However, to read non-textual data, a Brainfuck program may need to distinguish an end-of-file condition from any possible byte value. Thus 16-bit cells have also been used. Some implementations have used 32-bit cells, 64-bit cells, or bignum cells with practically unlimited range, but programs that use this extra range are likely to be slow, since storing the value n into a cell requires I copyright n time, as a cell's value may only be changed by incrementing and decrementing. In all these variants, the and commands still read and write data in bytes. In most of them, the cell's wraparound, that is incrementing a cell which holds its maximal value, will bring it to its minimal value and vice versa. The exceptions are implementations which are distant from the underlying hardware, implementations that use bignums, and implementations that try to enforce portability. Fortunately, it is usually easy to write Brainfuck programs that do not ever cause integer wraparound or overflow, and therefore don't depend on cell size. Generally this means avoiding increment of plus 255, or avoiding overstepping the boundaries of minus 128, plus 127. For more details on integer wraparound, see the integer overflow article. Array size: in the classic distribution, the array has 30,000 cells, and the pointer begins at the leftmost cell. Even more cells are needed to store things like the millionth Fibonacci number, and the easiest way to make the language Turing complete is to make the array unlimited on the right. A few implementations extend the array to the left as well. This is an uncommon feature, and therefore portable Brainfuck programs do not depend on it. When the pointer moves outside the bounds of the array, some implementations will give an error message, some will try to extend the array dynamically, some will not notice and will produce undefined behavior, and a few will move the pointer to the opposite end of the array. Some trade-offs are involved. Expanding the array dynamically to the right is the most user-friendly approach and is good for memory-hungry programs, but it carries a speed penalty. If a fixed-size array is used, it is helpful to make it very large, or better yet let the user set the size. Giving an error message for bound violations is very useful for debugging, but even that carries a speed penalty unless it can be handled by the operating system's memory protections. End-of-line code: different operating systems use subtly different versions of ASCII. The most important differences in the code used for the end of a line of text. MS-DOS and Microsoft Windows use a CRLF, that is a 13 followed by a 10, in most contexts. Unix and its descendants, including Linux and Mac OS X, use just 10, and older Macs use just 13. It would be unfortunate if Brainfuck programs had to be rewritten for different operating systems. Fortunately, a unified standard is easy to find. Urban Müller compiler and his example programs use 10, on both input and output. so do a large majority of existing Brainfuck programs. And 10 is also more convenient to use than CRLF. Thus, Brainfuck implementations should make sure that Brainfuck programs that assume new line equals 10 will run properly. Many do so, but some do not. This assumption is also consistent with most of the world's sample code for C and other languages, in that they use \n, or 10, for their new lines. On systems that use CRLF line endings, the C standard library transparently remaps \n to \r\n on output and \r\n to \n on input for streams not opened in binary mode. And of file behavior, the behavior of the comma command when an end-of-file condition has been encountered varies. Some implementations set the cell at the pointer to 0, some set it to the C constant EOF, some leave the cell's value unchanged. There is no real consensus. Arguments for the three behaviors are as follows. Setting the cell to 0 avoids the use of negative numbers, and makes it marginally more concise to write a loop that reads characters until EOF occurs. This is a language extension devised by Panu Kaliakowski. Setting the cell to -1 allows EOF to be distinguished from any byte value, which is necessary for reading non-textual data. Also, it is the behavior of the C translation of comma given in Ma1/4 layers Riordan file. However, it is not obvious that those C translations are to be taken as normative. Leaving the cell's value unchanged is the behavior of Urban Ma1/4 layers Brainfuck compiler. This behavior can easily coexist with either of the others. For instance, a program that assumes EOF equals 0 can set the cell to 0 before each comma command, and will then work correctly on implementations that do either EOF equals 0 or EOF equals no change. It is so easy to accommodate the no-change behavior that any Brainfuck programmer interested in portability should do so. Derivatives. Many people have created Brainfuck equivalents or Brainfuck derivatives. Some examples, pi, which maps Brainfuck into errors in individual digits of pi. Verbose-fuck, which looks like a traditional programming language. Only what appears as parameters or expressions are actually parts of longer commands that cannot be altered. Ook, which maps Brainfuck's 8 commands to 2-word permutations of ook. Ook. And ook. Jokingly designed to be writable and readable by orangutans according to its creator, a reference to the orangutan librarian in the novels of Terry Pratchett. However, there are also unnamed minor variants, formed possibly as a result of inattention, of which some of the more common are, forbidding, rather than ignoring, any non-command characters in Brainfuck programs, introducing a comment marker which comments out the rest of the line, various alterations of the loop semantics, sometimes destroying Turing completeness, requiring a special character to mark the end of the program, references. External links, Brainfuck at DMOZ.